In this video, I'm going to derive the F is equal to gamma Z bar A formula for fluid pressure. In a previous video, I used the formula and told you about it, but I didn't derive it. It's interesting deriving it. It helps you appreciate the general fluid pressure problem even more. So this is the handout that we looked at the other day. And the resulting force is equal to gamma Z bar area formula can be used for a variety of different problems, but it's especially helpful for the kind of problem where you have like a circular plate, a triangular plate, a parabolic plate, a half circular plate, basically a plate that doesn't have a constant width. The pressure distribution on this kind of plate, this is an example. So this is basically kind of like a circular plate, and the pressure varies with depth on that plate. And we don't have a formula that gives us the volume of that pressure distribution. So remember, the resultant force is the volume of the pressure distribution. And for a simple flat plate, constant width, you have a triangle or you have a trapezoid, and it's relatively simple problem. But again, this kind of problem is not easy. And so one alternative is to integrate it. And I've already done some integration. I'm going to do some more examples here in a little while. But again, this is a complex problem, but that F is equal to gamma Z bar A formula applies to this. And it's a pretty simple approach. So again, these are the cases that we're looking at: a circle, triangle, parabola, half circle, or whatever. And the formula is basically, we're calculating the resultant force. And so the gamma is the specific weight of the fluid, whatever that is. Z bar is the depth from the free surface down to the centroid of that shape. And so the centroid of a circle is just the radius. The centroid of a triangle is 1/3 of h. The centroid of a parabola is 2/5 of h down from the top. And the centroid of a half circle is 4r over the 3 pi from the top of the half circle. Now, again, you're taking it down from the free surface, and so the fluid level might be higher than that. And so you have to take the fluid level down to that point. So you might have to add some depth to it. So that's Z bar. Gamma, again, is the specific weight. And then finally, the area is the area of the plate. And so if our circle, if our plate is a circle, then the area is pi r squared. If our area is a triangle, then the area is 1/2 base times height. So the width of the triangle and the height. For a parabola of this shape, the area is 2/3 of base times height times 2, depending on the base. But basically, if the base is half of the formula, if you cut this parabola in half, as shown down here, where the base is this and this is height, the area is twice that. And again, for a half circle, the area is pi over 2 times r squared. So again, these are flat plates of variable width. Now, this is an important point. I didn't mention this the other day, that we're calculating FR, the resulting force, and we're using the depth to the centroid of the plate. But FR doesn't act at that centroid. FR acts at the center of pressure, P, which is lower than the centroid of the area. So if you notice, for each of these shapes, I drew a C, which is the centroid, but an FR at P, which is the center of pressure. So C and FR lower, C, FR lower, and so on. And I'm just trying to reinforce the point that FR acts at the center of pressure, which is below the centroid. That's one of the confusing aspects of this formula, because you use the Z bar, but that's not the location where FR acts. You use the Z bar to calculate FR, but FR doesn't act at Z bar. It acts below it at some P. Now, that's the limitation of this method. So the limitation of this method is it actually doesn't give you the location of FR. It gives you the value of FR. And of course, that formula is easy. It's easier than integration. But if you can use integration to find the location of FR, and that's really the only way to do it. But if all you want is the value of FR, this is obviously way easier than integration. So again, this is our formula. FR is equal to gamma Z bar A, X at the center of pressure. And so again, the plate could be at any depth. And so the plate can be right at the surface where the pressure at the top of the plate is 0, and the pressure at the bottom of the plate is some, in this case, some depth. Or the plate can actually be, some depth down. So Z bar is equal to Z down to the top of the plate plus the distance to the centroid there. And the plate could be at any orientation. These are drawn mostly vertical, but the plate could be at a different orientation. So let's derive the formula. It's actually an interesting and relatively simple derivation. It's very clever. So this is basically the same derivation that Hibbler gives in his book. And so you take a general plate at an arbitrary angle. The top of the plate is at a depth Z1. The bottom of the plate is at a depth Z2. You have a smaller pressure at the top, which is gamma times Z1. You have a larger pressure here at the bottom of the plate, which is gamma times Z2. And of course, the pressure varies with depth along the plate. And if you look at an arbitrary area on this plate, basically an area dA, and that dA is some depth Z from the free surface, the pressure at that depth is gamma times Z, and it acts on a dA. So it's a pressure on a dA. So remember, the most fundamental equation that applies to every fluid pressure problem is that the FR is the volume of that pressure distribution, and it's the integral of all of the PdAs across the face of that plate. Those pressures act perpendicular to the plate. That's one of our rules of pressure. And of course, our other rule of pressure is that pressure is a function of depth. So integral PdA. But if pressure is gamma times Z, you could actually pull the gamma out of the formula. And so FR is gamma times the integral of Z dA. But if you look at that integral of Z dA, that looks familiar. It's the first moment integral. And if you remember our definition of the centroid formula, so a centroid Z of an arbitrary area relative to some axis is the integral over the area of Z times dA divided by dA. And so the numerator is a moment equation, and the numerator is basically just the area of the plate. And so if you multiply through by this denominator, you get the numerator, which is the integral of Z dA, is equal to Z bar times the integral of dA. But the integral of dA is the area. But if you look at this integral of Z dA, that's the same thing as so FR is gamma times the integral of Z dA. But if the integral of Z dA is Z bar times area, then our FR formula is gamma times Z bar times A. And so it's a relatively simple derivation. It flows from our centroid definition, and it also flows from the principle that remember that FR is the volume of the pressure distribution, which is the integral of pressure times dA, or the integral of gamma times Z times dA. And again, this is independent of the orientation of the plate. It's independent of how deep the plate is. As long as you take Z from the free surface down to an arbitrary area in the plate, it works. Pretty cool, pretty fascinating. And so again, FR is not the pressure at the centroid. FR acts below that at the center of pressure P. Even though we use the centroid, PEFR doesn't act at that point. That's a conceptual question that you may see on a test at some point. So now we're going to apply that formula again. I think we worked the triangular formula before, but let's do it again. This is a triangular plate. The Z bar, it's 1 meter deep, 1 meter wide. A Z bar is 1/3 of 1 down here, 1/3 meter. This is fresh water, so our rho is 1,000 kilograms per cubic meter. Gamma is 9.81 times that, which is 9810 newtons per cubic meter. So FR is the pressure at Z bar times the area times gamma. So gamma is 9810, Z bar is 1/3, and our area is 1/2 of the base, which is 1, times the height, which is 1, and you get 1.635 kilonewtons, which is the same number that we got from integration. Here's a round tank from an old exam. Here's a round tank that has a radius of 0.5 meters. It's centered at the origin of the XY axis. The equation is defined as x squared plus y squared is equal to 0.5 squared. And we want to find, and this is, again, the end of a tank. It's filled with water. And so we want to find the resultant force on the side of this tank. It's not easy to integrate it, but the gamma Z bar A equation makes it really easy. So rho is, and for this problem, is 1 megagram per cubic meter, which is basically 1,000 kilograms per cubic meter, times 9.81 is 9810 for its fresh water. Z bar is 1/2 meter, and the area is pi times 0.5 squared. So FR is gamma times Z bar times area, which is 3.85 kilonewtons for FR. Pretty straightforward. And finally, this is one of your homework problems in Hibbler. And so this is a parabola. It's 4 feet deep, and it's 4 feet wide at the top. Y is equal to x squared. The Z bar down from the top of this guy is 2/5 of h, or 2/5 of 4, which is 0.4 times 4, which is 1.6 down from the top. The area is 2 times 2/3 BH. And so 2/3 BH is 2/3 of 2 times 4. And finally, FR is gamma times Z bar times area. And you get FR is 426.7 pounds. Way easier than integrating. I earlier worked an example problem where we used this for 3 different ways. And so here's actually another problem 3 different ways, or 2 different ways. Actually, this problem is 2 different ways. So this is a square plate. This is the general squared plate problem, but the problem I worked last had a triangular distribution on it that came up to the surface. But this one is a rectangular plate that's below the surface, and so it has a trapezoidal pressure distribution on it. So the top of this plate is 6 foot deep. The plate is at a 3-4-5 slope. So the length of the plate is 5 feet. We're talking about the width of this plate is basically 1 foot into the board this way. Always remember, always pay attention to the width of your plate. So this one is just 1 foot into the board. This is fresh water. So our gamma is 62.4 pounds per cubic foot. And so the pressure at the top of the plate, we're going to work this 2 different ways. So the pressure at the top of the plate is 6 gamma. The pressure at the bottom, so the total depth is 6 plus 4, which is 10. So the pressure at the bottom of the plate is 10 gamma. And notice how we just refer to the pressure as a depth times gamma. It just makes the numbers simpler. So the resultant force is the average of 6 gamma plus 10 gamma. So 6 gamma plus 10 gamma divided by 2. So 16 gamma divided by 2, which is 8 gamma, times the length of this guy, which is 5, times the depth into the board, which is 1. So you get 8 gamma times 5, which is 40 gamma. And if you multiply 40 times 62.4, you get 2.5 kip or 2,500 pounds is the resultant force. The location of FR, uh, we can use the trapezoidal formula for that. And the kind of the standard formula that I gave you on the centroid formula sheet is Y bar is 1/3 of 2P1 plus P2 divided by P1 plus P2 times L. And so if you plug our numbers from this problem into that, it's 1/3, 2 times 6 gamma plus 10 gamma. The gammas actually all cancel out. And you're left with Y bar is 2.29 feet. And this is measured from D. It's measured from the bottom of the plate upward. And so it's 2.29 upward, measured upward. And so remember, this is a 5 foot long plate. So 2.29 up is below the center of the plate. And again, it's 2.5 kip. Okay, so using the F is equal to gamma Z bar area equation, you basically have FR is gamma, which is 62.4. Z bar is the depth of the center of the plate. So the depth of the center of plate is 6 plus half of 4. And so it's 8 feet to the center of the plate times the area. And the area of this plate is 5 times 1 into the board. And so if you take gamma, Z bar, which is 8, area, which is 5, you get 40 gamma or 2.5 kip. And so basically the FR is very easy this way. It's easy both ways, really. You could argue it's easier with the gamma Z bar A equation. And again, but unfortunately, it doesn't give you the centroid. So if we want the actual center of pressure, if we actually want the location of FR, then our gamma Z bar equation doesn't help us. We have to go to this guy, or we would have to integrate if it's an integration problem. And so again, this is a derivation of the F is equal to gamma Z bar area equation. And I think it's good to know because it utilizes the centroid definition of the integral. I think it's kind of interesting.